put the number 11, then write down verification of the relationship between the mass of a body suspended from a helix spring and its period of oscillation So this is a similar practical to the one I discussed before, right? This is similar, so this won't take that much time, right? So for this experiment, you can take this down. You have to use a stand like this. There's a clamp. You hang it here. Then you have the helix spring. Now the locating pin is here like this, right? I'm not mentioning materials and apparatus, those stuff, right? Because those are already in the book, right? So what do you do in this experiment? So this is the stand, right? This is the stand. Then you hang a helix spring. Then you put some weights on this, right? Weights on this. Then that spring is stretched. Spring gets stretched, right? Depending on these weights. Then to the equilibrium position, once this stops, right? We are not oscillating this yet. We have to first find the equilibrium point. When this is at rest, this extends and comes to rest, right? Then you have to place the locating pin here like this. Okay. Then what do? You give this a small, then you extend this further, then release. Then it starts to go on a simple harmonic motion like this, right? Using the locating pin, you can determine those oscillations, right? Similar to the previous one, right? So the previous what we discussed applies to here as well. Okay. So we don't have to discuss that much on this experiment. Okay. So do you remember the time period for this one? This equation, right? T equals 2 pi mass divided by K is what? K is spring constant, right? If you don't remember, take those down. K is spring constant. Simple M is the loads applied here. Mass applied here. Simple M divided by K, 2 pi. That is time period. Time period means this goes up. It has to complete one cycle. Goes up, comes to the original position. Goes up, comes to the original position. So that is a one time period. Here as well, you have to take for like 40 oscillations in order to minimize the fractional error. Everything discussed earlier applies here, right? Okay. So if you read, you can take this equation down. So if you read the title carefully, what do you say? Verification of relationship between mass of a body, that is simple M, and time period. So this experiment, target of this experiment is what? To say that this equation is right, correct, right? So how do we say an equation is right? Whenever you have to make sure that an equation is right, you have to go for graphical method, right? So that is the another reason for going for graphical method. There's no any other experimental method to say that the equation is right. You cannot just put two numbers and say that this equation is right. You have to verify the equation, right? To verify the equation, in any case, you can check any practicals, right, on the book. For all the verifications of equations, you always have to go for graphical methods. You always have to go for graphical methods, right? Here the same. Right. Here we are not going to find simple k or anything. We have to verify this, right? That's the reason for using a graphical method. Below that, right? Why graphical method? Why graphical method? Below this, right? Here, the target is not, here the target is not minimizing, the target is not minimizing the random error. The target is not minimizing the random error. Verification of equations, verification of equations experimentally must be done using graphical method, using graphical method. Okay, using graphical method. I have to say the same stuff, right, in this experiment as well. I'm not going to, but I'll explain some. Okay, so here also I can say like this, right? Root m, you can take root m as x and t as y. But what's the problem here? This is less accurate, right? Same as before. That's why we have to square both sides. To prove that we need error analysis, right? That is out of the syllabus. But saying this is more accurate is enough. 5 squared divided by k m. So this is used as y, this is as x, and this is as m. This is more accurate. Take it down. So we square this both sides, right? Then we have to get 6 readings for each t squared and simple m. Simple m is the mass applied, right? So let's say you put a 1 kilogram here. Not a 1 kilogram, right? It is like 50 grams. For an example, I'll take, you put a 1 kilogram here. Then, same as before, you have to take the time measurement for 25 oscillations. So let's say, for simple M, you put a 1M here, then you get time measurement for 25. So you do that for 3 times, right? Then you have to determine that for one oscillation. Then you divide by T1 by 25 or 40, right? Whatever recommended. So T1, T2, T3. Then what do you get? Then you get average. That is T. Then you get T squared. If you want, you can write this with me. T equals T1, T2, T3 divided by 3. Then you need to get T squared. So likewise, all you have to do is just increase. So once you do this, so now you have done this experiment 3 times, right? For a one mass without changing anything, then got the average value, then got the T squared. Then you have one value, right? One coordinate. T squared means Y, M is X. Then what do? You get 6 such readings. You have to repeat these. It is like you have to do this 18 times, right? Understood? You have to measure. It is not that easy. You have to do the same thing. Same thing means by slightly changing M, you are taking 18 time measurements, right? In order to get this. So once you get that, so you have T squared values here and X values here. You draw this graph between T squared and M. Then you have 6 coordinates like this, right? Then what do? You draw the best fitted line. Best fitted line. The line that goes right in between, right? These coordinates. So if you get a straight line, what does it say? This is a, if you get a straight line which goes through the 0, it is proved that this is y equals mx. Now y equals mx is justified, right? So if this is verified, this is verified. If this is verified, this is verified. You go back. So that's how you do verifications, right? That's how you do verifications. Okay, take this down. So the same things applied, right? Here, for taking time measurements and all those stuff. You start from 3, 2, 1, 0 like that, 0, 1, 2, then 25 like that, right? Everything applies here. Okay. Right. Below this, right? Below this whole thing, right? All the important facts are discussed. All the important facts are discussed under 10th experiment. Under 10th experiment. right? So that is all the theories. Then I'll move on to doing a few past paper questions. Okay. So if you have chance, I mean, I don't know whether you have done this experiment at this school yet or not, but if you understand this, these are the like many times they ignored these. That's why this experiment seems like not that scientific, right? Sometimes you may feel that experiments are not that scientific. They are just taking values from here and there, but everything has a reason there, right? Taking there, this experimental side is a whole another side of physics. Okay, there are two main parts of physics. That is theoretical physics. Theoretical physics is that's what we are doing when you are doing questions. That is same somewhat theoretical physics. Another part is experimental physics, right? When you are going for like a PhD or something, those are two branches: experimental physics and theoretical physics. So this experimental side is, so everything given in theories must be proved using experiments. Otherwise, those theories are not considered valid, right? Those are just theories. That's why these experiments, they give a very important position for these experiment questions, right? Okay. Uh, then we'll do some questions. Just download. I sent you that a separate one that is 2006. Do you have that? Take that PDF 2006. It is in the group. So simply part 1. So they are asking just for the expression for time oscillation. So obviously this one, right? That's easy. Second part, rearrange the above expression in the most suitable manner in order to obtain a value for G by plotting a graph. Most suitable manner, right? Okay. So you have to square. When they say most suitable manner, this manner. You cannot put G here. You have to put G like this. So this becomes Y. This becomes X. This becomes gradient. Here the B is at the lowest point, right? I don't know whether the diagram is tilted, but B is the lowest point, okay? When taking readings for T, reference pin directed at point B shown above diagram. Why the directing of this B gives a better accuracy for time measurement than directing at A? That another thing is you should be able to form sentences to say what you mean, right, correctly, to convey your idea. So that comes with practice by doing questions, right? So what do you say there? Hmm? So for the better, you can just say at B, Bob has the highest speed. They don't expect further clarification why this is. You can just say at B. If they ask, you can say, but this is enough, right? At B, Bob has the highest speed. If you want, you can write due to less uncertainty. I mean, due to minimal time error of uncertainty, right? But here that is enough. Anyway, you have to answer exactly what they say, right? Okay. Part 1. Student measure the time for only one oscillation. That value is given as 2 seconds. Instrumental error. So that is the least count, right? That is delta t. They said 0. What? 0.1 seconds. Percentage error. So how do you find delta t divided by t? This is fractional error of time period, right? Not time measurement, not time for 25 oscillations. This is for time error for time period. Make it a percentage error, you have to multiply that by 100%. So delta t is 0.1 to 100%. 5%, right? Then at the second part, then he measures the time for 50 oscillations. Sorry, 25 oscillations. He gets 50.2 seconds. And here as well, least count, we are using the same measuring instrument, right? So the least count is 0.1 seconds. Then again, you have to calculate percentage error. Delta t divided by t, 100%. Zero 0.1 divided by 50.2 times 100%. Here you don't have to use logarithm, right? Do you see that within brackets they say only to first decimal, accuracy is required only to first decimal. So if they ask that, you can consider that this to be 50, right? This to be 50, because 50.2 will give a different value for like third decimal or second decimal. For the first decimal, we get the same value whether it is 50 or 50.2, it doesn't matter. So better to take 50 there. You only need the accuracy for the first decimal. So if it is 50, it is 0.2%. That is the fractional error. For the measurement of, for how many? 25 oscillations, fractional error is 0.2. Here the fractional error is 5%. Okay. The recommended fractional error is, it should be less or equal to 1%, right? This is okay, 0.2. This is not. That's why we take for 25 oscillations. Okay, in the part C, they are saying that the bob has a radius, right? So you have to rewrite the expression. So what is that? T equals 2 pi. Instead of L, you have to put what? I told you that it should be the distance to the gravitational point, right? Center of gravity. So it should be, instead of L, it should be L plus R divided by G root. Actually, you have to rearrange this. Rearranging means you have to make this in order of y equals mx plus c. So here the x variable is length, right? Length of the string. So take L out plus, then multiply this 4 phi squared R divided by G. So this is y, this becomes m, this is x, and this is c. Okay. So this is the answer for first part. Then second part, determine simple g. Determine simple g. So once you draw this graph, you can get gradient and the intercept, right? So in order to determine g, you can use gradient, right? Not intercept, because intercept has simple r. We don't know value for simple r. But everything in the gradient we know. So to determine simple g, we can find gradient. Gradient is given, right? Gradient is given as 4.0 s squared per square meter. No, per meter. So 4 phi squared divided by g equals to 4. These simplifications are easy, right? They don't make it complicated. Simplification is easy. But some cases they might give a complicated, but rarely, right? So if they take this pi to be 3.1, take it to be 3.1, right? You have to follow exactly what they say. Don't write 22/7 or something. You have, because they are saying a convenient method. They are giving you a hint, right? So if you follow those, you can easily conveniently get the answer, correct answer. You have to follow exactly they say in the question. Okay, 4 cancels off. Cross multiply g is equal to pi squared. Pi squared means they say 3.1. You can easily multiply 31 by 31, right? So 1, 3, 3, 9. 961. So 2 decimals, there are 2 decimals. So it should be 9.61. This is G. But if you put 22/7, this gets complicated, right? Understood? We don't need any complications. Okay, then you have to find the radius. To find the radius, you need to go for the intercept, because intercept includes the radius. So 4 phi squared r divided by g is equal to what? 0.04. Right. Here also, when you are doing the calculation, you have to do it simply, right? Don't make it complicated. You always have to go for a search for a easy method, right? So if you think about here, what is G? G is pi squared, right? You got that. You can use that here. Then pi squared cancels off. But if you substituted pi to be like 3.1 or something, then this calculation gets complicated, right? So in the exam, that's why you take students complain all the time that they don't have enough time, right? The reason is the lack of knowledge and lack of practice of doing questions, right? So pi squared cancels off, then 4r is equal to 0.04. So r is what? 0.01 meters. So that is a 1 centimeter, right? So radius of the bob is 1 centimeter. Right. In the part D, they say instead of a metal bob, so what we use is a metal bob, but student uses a wooden bob. So what happens? A wooden bob is, it has less density, so it has a less mass. I mean, yeah, mass is less, right, for a wooden bob. So what happens if it is a wooden bob? You know, we give this oscillation, you know, half mv squared. If this has less mass, the energy contained in the bob is less. So what happens? So the air, there are drag forces on air, resistive forces. If the wooden bob has less energy, its oscillation would quickly stops, right? Understood? Its oscillation quickly stops and it comes to rest, and we cannot do the experiment then. You can write a reason, but it has to be just reason, right? You should be able to justify that, right? You can be creative and write that. If it seems correct, they cannot reduce marks. But you should be able to justify that. So you can write energy stored in a wooden bob. Energy stored in a wooden bob is less compared to a metal bob. Is less compared to a metal bob. Right? Okay, so that is the experiment, the question on 2006. Then I sent you a PDF, check that, another PDF. Get the 2008. All the practicals are included there, right? Take 2008. Okay, 2008. We have this spring, so you don't get the exact experiment, right? There can be slight deviations. So you need to measure the extension of the spring. So this is given. So how do you place the ruler? It's placed like this, right? So this is the meter ruler. Mark these calibrated marks. So this becomes the meter ruler. Okay. So that is what you have to draw. Okay, simple B part. Simple B. Extension versus load. Extension, there's a factor 10 to the power minus 2 meters. Load is 10 to the power minus 3 kilograms, right? So whatever the coordinate you take, you have to multiply that by these numbers, right? If it is a mass, 10 to the power minus 3. If it is extension, 10 to the power minus 2. Okay, so what do they ask? So using this graph, so this is a graph between mass and extension, right? Remember this equation? This is the spring constant, okay? So they ask you to determine spring constant in kilograms per meter, right? So you have to get the gradient of this graph. Actually 1 over gradient becomes the answer there. So listen now, right? This is important. I don't know whether you know this or not. So when you get a graph, I didn't explain this. So this is applicable for all the graphs, right? For all the experiments. So when you are calculating gradient of a graph, you have to get two xy coordinates. You have to get two xy coordinates, right? One coordinate here, one coordinate here. Let's say x1, y1, another one x2, y2. So what is the gradient? Difference of y coordinates divided by difference of x coordinates. Then this gives the gradient, right? So there are rules when you are taking these coordinates. There are rules, right? You cannot choose these two coordinates to be very close. You have to use the whole graph. Another thing is, you can see the squares, these lines. The graph must go through intersect of the square net, right? You cannot choose these points, right? If it is fractionally intersects, you cannot use that. The graph should exactly go like this, right? So if you consider all those, you can find the most appropriate 2 points on the graph. So this point, the most appropriate point is x coordinate 70, y coordinate is 9. 70 and 9. Sorry, 72 and 9, right? 72 and 9. Sorry, 72 and 9.3. this coordinate. If you carefully look at 72 and 9.3. Another coordinate is this point. It is 9 and x coordinate is 9, y coordinate is 0.9. Okay. So these two are the most appropriate coordinates in order to find gradient, right? So these are the distances points, right? These are the apart points, most apart points, right? There are some other points here as well, but you can take this as well. They would give marks. Right. So using these xy gradients, you can find the xy coordinates, you can find the gradient. How do you find the gradient? So xy, y is 9.3 minus this y is 0.9 divided by x, 72 minus 9. So you know y coordinates must be multiplied by 10 to the power minus 2, right? Then x coordinates must be multiplied by 10 to the power minus 3. So what is the unit of this? Y divided by x. Y is measured in kilograms, x is measured in meters. So the kilogram divided by meter. You get the gradient as 63 divided by 84 kilograms per meter. You get the gradient like this. 63 divided by 84 kilograms per meter, right? But the spring constant, they ask the spring constant in terms of what? Sorry, not kilograms, meters per kilogram, right? Here these are the lengths. These are m. M means x coordinates. Y divided by x, meters. You get the gradient in meters per kilogram. But you need the spring constant in terms of kilograms per meter. Here it is not newtons per meter. They say it is they ask that in terms of kilograms per meter, right? So instead of newton, you have to take that in terms of kilogram, right? Not newtons per meter. So when you divide this, 63 means 63 has 7 nines. No. 1, 2, 1, 8, 3, 4. So it is 3 divided by 4, 0.75 meters per kilogram. So this is the gradient. So it is obvious spring constant should be 1 over gradient, right? Spring constant is 1 over gradient. So it is 1 over, no, here you get 84 divided by 63. 84 divided by 63. So you get 4 over 3 kilograms meters per kilogram. Here spring constant is 1 over gradient, meaning 4 over 3. So you get 3 over 4 kilograms per meter, which is 0.75 kilograms per meter. So this is the spring constant, 0.75 kilograms per meter. Then at the second part, they say clearly indicate on the graph the 2 points which you have used to determine K. So you can put these 2 points, right, as P and Q. This point and this point. Okay, then take part C. Try part C. Okay. So they have given, so instead of this equation, they have given a modified equation, right? So if they say take this equation, you take that equation, right? You don't have to argue with that equation. You just follow everything they say in the question, right? So they have given a modified equation, and they, because it is spring constant and multiplied by G. Remember, we got the spring constant in kilograms per meter. To make it Newton, you have to multiply by G, right? That's why there's a G here. But you don't have to think about those stuff, right? You just take the equation, whatever they say, right? Then all you have to do is, you just have to arrange this in order to draw a graph. So what do we do? You make it squared. 4 squared m plus divided by kg. Put kg here, right? You square this and put the kg here. Then bring out the brackets. 4 phi squared capital M divided by kg plus 4 phi squared kg m over 3. So this one you can take it as y. This one you can take it as gradient. This one as x. And this whole thing is c. Now you have rearranged this. Because of this term, there's a intercept in the graph. So this is the first part of C. If you have a problem, let me know, right? C first part. Second part. What additional instruments do you need to take measurements in this experiment? So in the experiment, so they're asking what are the measuring instruments, right? You have the meter ruler. So what is the another measuring instrument? Stopwatch, right? They haven't mentioned a stopwatch earlier. They have a meter ruler, but they don't have a stopwatch. So stopwatch should be the answer for the second part. Then the third part, what quantities would you extract from the graph to determine G and M? So you have to determine G, right? We already have calculated K. K is we found, right? So K is known. So to determine G, right? Yeah. You don't have to know about intercept, because intercept has an unknown simple m. Simple m is the mass of the spring, they say. You don't know simple m. So to determine simple G, you can determine that using what? Gradient only. So if you substitute values here, you can find G. Got it? They are not asking for the calculation. So the only unknown in the gradient is simple G. So you can find that if you know the gradient. Then you need to determine mass of the spring, simple m. So this equation got modified because they considered the mass of the spring. In the experiment, right? In the experiment in this book, this mass of the spring is considered to be negligible. But here they consider that, right? If they consider, they give you the equation. You don't have to remember this, right? They give you the equation. Then you just have to follow the instructions they say. Okay, so to determine simple M, what do we need? Simple M is included in the intercept. So simple M can be found using intercept. If the intercept is known, only unknown in this term is simple M. So you can find simple M. Understood? Thumbs up, right, if you understood. So let me know if you have any problems. Do you have? If the percentage error of mass value is 1%, how many oscillations would you need to take in order to match the percentage error of time period also to be t? And they have given an equation for percentage error of time period, right? So you have to use that equation, right? So they say this is the fractional error of time period. There's a 2 as well, right? You don't have to think about that. If they say so, you have to take so. So you know that 2 delta t over t is equal to what? Delta simple t over t. Earlier, remember? Delta t over t is equal to delta t over t. We got that in the note, right? So instead of delta t over t, you can put delta simple t over t. And there's 2 here. So what they ask is how many oscillations required. So this error is 1%. So this error has to be 1%. 1% means if you write it as a fraction, it is 1 over 100, right? 1% means 1 over 100. So error in the measurement, that is the least count, is given as 0.1 divided by time. What is this simple t? Simple t is equal to n times oscillation. So n times 1 oscillation takes 2 seconds. So this is 1 over 100. Then 2 cancels off. If you cross multiply this, n is equal to 10. So in order to make the error of time period to be 1%, you have to at least take 10 oscillations, right? 10 oscillations. Okay, take it down. Once you are done, thumbs up. Okay, then part E. So student use a brand new spring. Then they say on the figure given below, sketch the shape of the graph that you would expect in this situation. So for the usual spring between E and M, you got a graph like this. If the spring is brand new, you have to think about this practically, right? If the spring is brand new, it is very hard to extend that, right? Initially, it's a bit hard to extend. So what happens, even though we increase the mass or the weight on the spring, extension, there's no extension. But the extension causes after certain value of capital M. Like that, right? If you have experienced a brand new spring, even though we apply force, There's no extension initially, right? Extension is 0. So the graph should be like this. Okay, just draw that one. After, you can try these questions again, right? Only way to get this, you have to practice doing these questions. So for structured essays as well, you have to separately practice for those. Same as MCQs and essays, right? So at home, try this one, right? 2015 A level. So this is based on simple pendulum, 2015 A level question. And if you have any problems regarding this question, 2015, please let me know. Send me a message, then I'll explain that. So on tomorrow, I'll be discussing of, tomorrow 8 p.m. I'll discussing of sonometer. So sonometer also has 2 practicals. Based on sonometer, there are 2 practicals. There are many questions. Oftentimes, they ask questions based on sonometer, right?